Morning everyone, myself Himanand Kumar. I'm doing m.tech from Tehsil University under Computer Science Engineering Department. Today I'm going to discuss about integer factorization. Introduction about what is integer factorization. Suppose we have an integer n that we wish to factor, that is to decompose into a product of primes. The primality test of the preceding section may tell us that n is composite, but it does not tell us the prime factor of n. Factoring a large integer n seems to be much more difficult than simply determining whether n is prime or composite. Even with today's supercomputers and the best algorithm to date, we cannot feasibly factor an arbitrary 1024 bit number. Here we will discuss pollard RHO heuristics. Before the starting pseudocode, one small introduction about pollard. Here trial division by all integers up to r is guaranteed to factor completely any number up to r square. For the same amount of work, the following procedure pollard RHO factor any number up to r to power 4. Here, since the procedure is only a heuristic, neither its running time nor its success is guaranteed, although the procedure is highly effective and practiced. So now pseudocode in first line, the procedure works as following: 1 to initialize I to I and x1 to a randomly chosen value in Zn. The while loop beginning on line 5 iterates forever, searching for a factor of n. During each iteration of the while loop, line 7 uses the recurrence x1 is equal to x1 minus 1 k square minus 1 mod n to produce the next value of xi in the infinitive sequence like x1, x2, x3, x4, so on. With line 6 correspondingly incrementing I, the pseudocode is written using subscripted variable x1 for clarity, but the program works the same if all of the subscripts are dropped. Since only the most recent value of x1 needs to be maintained with this modification, the procedure uses only a constant number of memory locations. Often, the program saves the most recently generated xi value in the variable y. Specifically, the values that are saved are the ones whose subscripts are power of 2. x1, x2, x4, x8, x16. Line 3 saves the value x1 and line 12 saves xk. Whenever I is equal to k, the variable k is initialized to 2 and line 4. And line 13 doubles it whenever line 12 updates y. Therefore, k follows the sequence 1 to 4, 8 and always gives the subscript of the next value sk to be saved in y. Line 8 to 10 try to find a factor of n using the saved value of y and current value of xi. Specifically, line 8 computes the greatest common divisor d is equal to gcd y minus x1 n. If line n finds d to be non-trivial divisor of n, then line 10 prints the d. Here, this procedure for the finding a factor may seem somewhat mysterious at first note. However, the pollard RHO never prints an incorrect answer. Any number it prints is a non-trivial divisor of n. It might not print anything at all, though it comes with the no or guarantee that it will print any divisor. However, that we have good reason to expect pollard RHO to print a factor p of n after root p iteration of the while loop. Thus, if n is composite, we can expect this procedure to discover enough divisor to factor n completely after approximately n to power 14 updates, since every prime factor p of n expect possibly the largest one is less than root n. See, we begin our analysis of how this procedure behaves by studying how long it takes a random sequence modulo n to repeat a value of z. The algorithm does not terminate at all but may print some of the factor of n. There is a good reason to expect that it prints a factor of n approximately after p power iteration. Here, once we reach an xi such that xi is equal to xz for some z less than I, we are in the cycle. Since xi plus 1 is equal to xz plus 1, xi plus 2 is equal to xz plus 2, and so on. The reason for the name RHO heuristic is that in given figure we can draw the sequence x1, x2, xz minus 1 as the tail of the RHO and cycle xz plus 1, xi as the body of RHO. Here the example given in the first diagram, the value produced by recurrence xi plus 1 is equal to xi square minus 1 mod 1387. Starting with x1 is equal to 2, the prime factorization of 1387 is 19 into 73. The heavy arrows indicate the iteration steps that are executed before the factor 19 is discovered. The light arrow point to unreached value in the iteration. They illustrate the RHO shape. The shaded values are the y values stored by pollard RHO. In the factor 19 is discovered upon reaching x7 is equal to 177. When GCD 73 minus 177 is equal to 1387, it's computed by 19. The first x value that would be repeated is 1816, but the factor 19 is discovered before this value is repeated. The values in diagram B, the values produced by the same recurrence modulo 19, every value xi given in part is equivalent modulo 19 to the value xi shown here. For example, both x4 is equal to 63 and x7 is equal to 177 are equivalent to 6 modulo 19. In diagram C, the values produced by the same recurrence modulo 73, every value xi given in part A is equivalent modulo 73 to the value xi. Here, by the Chinese remainder theorem, each node in part corresponds to B pair of nodes, one from part B and one from part C. The sequence xi induce a corresponding sequence xi modulo p, where xi is equal to xi mod p for all I. Here the reasoning of before, we find the expected number of steps before the sequence xi repeated is root p. If p is small compared to n, the sequence xi might repeat much more quickly than the sequence xi. Indeed, as part B and C of the given figure. The next slide. How long it may take for the sequence x1, x2, x3, so on to repeat. This is in here. The algorithm might not perform quite as expected for two reasons. First, the heuristic analysis of the running time is not rigorous, and it is possible that the cycle of values modulo p could be much larger than root p. In this case, the algorithm performs correctly but much more slowly than desired. In practice, this issue seems to be moot. Second, the divisor of n produced by this algorithm might always be one of the trivial factor I या n. For example, suppose that n is equal to pq, where p and q are prime. It can happen that the value of t and u for p are identical with the value of t and u for q, and thus the factor p is always revealed in the same GCD operation that reveals the factor q. The both factors are revealed at the same time. The trivial factor pq is equal to n is revealed, which is useless. Again, this problem seems to be insignificant in the practice. If necessary, we can restart the heuristic with the difference recurrence of the form xi plus 1 is equal to xi square minus c mod n. This analysis is heuristic and not religious. Since the recurrence is not really random, the procedure performs well in practice and it seems to be efficient as this heuristic analysis indicates. It is the method of choice for finding small prime factor of large number. The factor beta bit composite the number n completely. We only need to find all prime factors less than root n, and so we expect pollard RHO to require at most n to power 1 4 is equal to 2 beta 4 arithmetic operation and at most of the bit operation. Here p non-trivial factor of n such that GCD p n of p is equal to 1. Consider the sequence x1, x2, x3 so on where xi is equal to x1 mod p. We also have x1, x2 I minus 1 mod of p. Expected number of steps before the repeat is p root, the t index of the first repeated value, where u value is greater than 0, the length of the cycle that has been produced. Expected value of t and u are root p. We find the expected number of steps before the sequence xi repeats in the root p. If p is small compared to n, the sequence xi might repeat much more quickly than the sequence xi. Therefore, once pollard RHO has shaped as y any value as k such that the value of k is always greater than or equivalent to t, and then y mod p is always on the cycle modulo p. Eventually k is said to be a value that is greater than u, and procedure then makes an entire loop around the cycle modulo p without changing the value of y. The procedure then discovers a factor of n when xi runs into the previously stored value of y modulo p, that is when xi is equal to y of mod p. The factor found is the factor p, although it may occasionally happen that a multiple of p is discovered. Since the expected value both t and u are root p, the expected number of steps required to produce the factor p is root p. The algorithm might not perform quite as expected of the two regions which is already listed. Here eventually y will be sent to xi value on the cycle, and afterwards the whole cycle will be traversed without changing the value of y. When the value xi will be encountered, again a factor of n will be discovered. The sequence x1, x2, x3 may start to repeat much later than after the root p. Here expected number of arithmetic operation Tn is equal to root p. Expected time complexity is here Tn is equal to 2 to power beta 4 into big power 3. It's require one GCD computation for each step of the recurrence. Instead we could batch the GCD computation by accumulating the product of several xi value in the row. Then using this product instead of xi in the GCD algorithm. So okay, thanks for listening me.